Okay. I have written here a little bit about force method. So later you can go through and read it. But similar to the technique that you learned before this, like slope deflection and also the moment distribution technique, force method is used to analyze statically indeterminate structures that have more than 3 support reactions, and we cannot use only equilibrium equations to analyze them and obtain the internal forces. In addition to that, if your structure is under settlement or any type of deformation or rotation, you can use this technique in order to get the internal forces. There are different names given for this technique, but mostly it's referred to as force method. The reason is that first we use this visual work method to calculate the deformation, and then we normally transform our structure from a statistically indeterminate structure to a statistically determinate structure. Okay, so how this method works, if you have indeterminate structure and you want to analyze it, your first problem is that you have extra support reactions, for example. And if you have only 3 support reactions, you can easily analyze any structure by using sigma fx equals to y, or sigma m equals to 0, and you get the internal forces. So the way that we are going to deal with indeterminate structures is that first we convert them to a determinate structure. And then we get some compatibility condition. And based on those compatibility conditions, we can analyze and obtain the support reactions that we don't know their value. There is one step-by-step procedure that you can read it inside the note that I have given to you. I will explain this step-by-step procedure through the example that is given here for you, okay? So let's go into the technique and see how we can use it. Please give your 100% attention to this example, because this is the base. If you learn it well, you can apply to any given example to you. This is one structure that is given to us, and they have asked us to analyze it, again, the bending moment and shear force diagram. By first look, you can see we have 3 support reactions in point A because it is a fixed support, and we have 1 support reaction at point B because it is a roller support. So totally, we have 4 support reactions. And you know that if you have more than 3 support reactions, your structure becomes indeterminate. And we cannot analyze it by writing equilibrium equation. So this structure is indeterminate structure right now, and the degree of indeterminacy is 1 because we have only 1 additional support reaction that we cannot determine. We have 4 support reactions, we can write 3 equations, so 1 support reaction cannot be calculated. Okay, so this is the first thing that you need to understand about your structure, that what is the degree of indeterminacy of your structure, which is 1 for this structure. So this is very easy, just calculate the support reaction, minus 3, it gives you the degree of indeterminacy. Normally in the exam, we give you and the test a structure that has only 1 degree of indeterminacy, but here in the note I have already prepared example for the case that has 2 or even more degree of indeterminacy. You will see how we can deal with that case as well. But if you learn this one, you can apply it to any other time. Okay, so now we have one structure with 1 degree of indeterminacy. You need to select which support reaction you want to obtain, meaning there are 4 support reactions here. One of these support reaction is the one that if we know it, we can analyze the rest of the structure, right? For example, if you know how much is the support reaction at point B, let's say it is 10, then the other 3 can be easily calculated. Just right now, sigma m equals to 0 at point B, sigma y equals to 0, and then you can get the others. So the next step after you determine what is the degree of indeterminacy is to select one of the support reaction as the redundant support, meaning the redundant support, meaning that we want to calculate that support reaction. In the selection of that redundant support, what is very important is that if you remove it, the structure should remain still stable. For example, at this point, if I remove this support and I assume that this support reaction is the redundant one and I want to calculate this support reaction through the force method. So if I remove the support reaction, I get the cantilever beam, which is still a stable structure. So I can select that one. Normally in the test and in the exam, we will tell you which support reaction should be selected as the redundant. But if it is not given, sometimes we ask you to tell us what are the support reactions that we can consider them as a redundant support reaction. In that case, you need to see which one is the one that if you remove it, your structure becomes unstable. I have some example in the next pages we will see. But for the moment, you just understand that the support reaction that you want to consider it as a redundant is the one that shouldn't make your structure unstable. Like the support reaction at point B here, that if you remove it, still the beam is a stable structure. Okay, so two steps right now have been already explained. One is to determine the degree of indeterminacy, and the second one to select one of the support reaction as the redundant one. And your job is to calculate the value of that support reaction through force method. The moment that you get the value of that support reaction, your structure becomes a determinate one and you can easily analyze it. For this specific case, we have assumed that XB, or the support reaction at point B, is the redundant support reaction. And our job is to calculate this XB. So our focus from now on is on XB, and we want to know how we can get the XB, support reaction at point B. Okay, in order to get XB, we are going to have a trick here. What is our trick? Our trick is that we are going to remove XB. If I remove XB, my structure turns to be a cantilever structure, which is a determinate structure. So this determinate structure can be easily analyzed because it has only 3 support reactions. I can get the bending moment, shear force, and I can calculate its deflection using the virtual work method. But the problem is that if I remove XB, the beam is going to have a deflection. Let's call this deflection delta BO. This deflection in reality doesn't exist in the structure that I want to analyze because this structure has a support there and doesn't allow my structure to have any deflection here. So by removal of XB, I get a deflection that doesn't exist. I need to deal with this deflection. So in order to deal with this deflection, I will take the same structure out and put it down here. I will remove all the external forces. So external forces is going to be removed, but the beam itself is there. I will say that I'm going to apply a unit load to point B such that it imposes the deflection of delta BB. And if this delta BB equals to delta BO, then these two structures is going to represent the main structure. Why? Because in that case, if delta BB equals to delta BO, there is no deflection here. And if the deflection is not there, this beam is going to be represented by these two beams. But the problem is, I don't know how much force I should apply to point B in order to make the deflection exactly similar to delta BO. Because in the first place, we don't know how much is exactly the deflection of the structure. So this is why I assume that I can apply a unit load to point B, and I will multiply this unit load to a value of XB that I don't know how much it is. But what I want is that after multiplication, XB multiplied to delta BB should equal to delta BO. In that case, these two is going to represent the main beam. So I will repeat again. We have a beam which is considered to be an indeterminate structure. We want to analyze it. And in order to analyze, we select one of the support reactions to be the redundant one. That support reaction here assumed to be XB. In order to analyze the frame, I will remove the support reaction first. The moment that I remove it, the beam is going to have a deflection at that point. I call this deflection delta BO. I need to push back this deflection to its original location such that deflection becomes 0. In that case, if deflection is 0, then this beam is going to represent the real structure. So in order to do that, I'm going to apply a unit load to this beam. But in that beam that I have, there is no any external forces. Only a unit load is going to apply. I will increase the intensity of this unit load that much that delta BB become equal to delta BO. In that case, summation of these two is going to represent the real structure because I have a structure that doesn't have any deflection. It has the same load, and the support reaction also is going to be equal to the XP. So what we have written here is called compatibility condition, meaning if delta BB equals to delta BO, then we can say that these structures represent the real structure. As I said, since we don't know how much force we should apply here, we assume it to be XP. The moment that this XP the moment that this delta BB equals to delta BO, then this XP is exactly the support reaction that it has to be here. So this is the step-by-step procedure that you need to go through. You need to determine what is the redundant support reaction. You remove that support reaction. Your structure is going to convert it to a structure. One structure is going to be exactly like the first structure with the external forces. For that structure, you are going to calculate how much is the deflection at the point that you have removed the support. Then the second structure is going to be similar to the first one without any external load, no external load, but with one unit force applied to the location that you have removed the support. The direction of this force, unit load, is not important. It can be toward up, it can be toward down. You just need to apply a unit load there. Okay, after that, you get delta BO. You need to calculate delta BO using the virtual work method that we explained in our first part of our class. And then for the second structure, you need to calculate delta BB. The moment that you got delta BO and delta BB, you put it inside our compatibility condition and you get XP. XP is a support reaction that was not unknown for us. And the moment that you calculate these two, it can be a known parameter for us. So the moment that you got XP, then your beam is going to be a redundant, is going to be a statistically determinate beam, and you can calculate support reaction after that easily. Okay, so this was basically the theory behind it. So we are going to see a few examples to see how we can apply it in real structure. So before I go to the example, I just want to highlight to you two important things. If you want to analyze a structure through a force method, you need to select one redundant support reaction, and that redundant support reaction is going to be removed from your structure to make it a determinate structure. Then you need to calculate the deflection under that due to this external force that you have. And then you need to have a second structure, which is exactly similar to the first one, but without the external force. In the second structure, you are going to apply a unit load to the place that you have removed the support reaction. You calculate two deflections, one from the first structure and one from the second structure. You put it inside our compatibility equation, you get the unknown support reaction, and then your beam is determined. So this is what you need to do when it comes to force method. Now let's go and see one example. So the same structure just now we had, I've given here some values. The same structure is loaded by 3 tons per meter, is a uniform load. And then our job is to analyze this beam and get internal bending moment and shear forces. Okay, now let's see how we can do that. As we said, first we need to determine which one is going to be our indeterminate redundant support reaction. Normally we select the vertical support reactions, but you can select bending moment or shear force in the left side of this beam. The procedure will be completely similar. We will see in the next example. But since we are in the beginning of this method, so let's just make it easy for us. XB is going to be selected as the support reaction that we want to determine. So the redundant support reaction here is the support reaction at point B. So this is the structure, primary structure that is going to be analyzed. So we said in order to get XP, first we are going to remove this one. So if you remove it, your structure is going to have some deflection. In order to deal with that deflection, we remove the external force, we get a second structure, and we apply a unit load exactly to point B. So right now we have two deflections. If these two deflections equal to each other, then these two structures is going to represent the real structure. So we can write down our comfortability condition. Since we don't know how much force we should apply exactly to point B in order to make delta V equals to delta VO. So we multiply this one to XP, and then we can write down delta VO plus XP multiplied by delta VB should equal to 0 because we don't have any deflection here. There are cases, for example, you have settlement at point B. If you have settlement, let's say 3 centimeter, then you can put in the right side 3 centimeter settlement also is inside my beam. So these two summation should equals to 3. But since there is no settlement at point B, we assume to be 0. So that's why in the right side we have 0. Okay, if you look, in order to get XP, the support reaction that we are looking for, we need to calculate delta VO and we need to calculate delta VB. Delta VO should be calculated from the first structure, and delta VB should be calculated from the second structure that is exactly similar to the first one without external load, but with odd unit load. So we are going to do this calculation based on virtual work method that we learned. Meaning, if I want to calculate delta VO, I need to first, to analyze this structure, get the bending moment, and then I need to have a second structure without this external load and apply unit load to that location and get bending moment. That structure gives us M bar, this structure gives us M, and we put inside our integral and get delta VO. For the second structure, we need to do the same. So we are going to apply again a unit load there, and then we calculate M and M bar, and then after that, we can put it inside our equation and get delta V. So as long as we haven't calculated these two, we cannot get XP. Let's go and calculate delta VO and delta VB. This is exactly similar to the previous calculation. So don't forget, here we have two structures, and each structure has its own deflection that need to be calculated. So first we do the calculation of delta VO. This is what I have written here for you using the virtual work method. So for this structure, since we have only one span, you don't need to divide it into several segments because the bending moment can be easily calculated by only writing one equation. So you can see that the origin of X is here. You cut it from here, like the one that you see, and you can calculate the bending moment. It's going to be 1.5 negative 1.5 x power 2. Okay, so this is the M. In order to calculate M bar, we need to remove the bending the load from our structure and apply a unit load over there. The direction of this unit load is not important toward up or toward down. At the end of the day, you get a positive or negative, and that is going to give you the sign of the basically the deflection. So we remove the load, we apply a unit load, and then again the origin should be similar to this first part. Since for the real beam the origin of X was from the beginning, for this one also should be from the beginning. So you can see 1 multiplied by X is going to equal to M. So M is going to be positive X. So right now you calculated the M and M bar for the first beam. And if you put it inside our structure, our equation, it can give you delta VO. So M is this one, M bar is this one. You put it there, you calculate the integral, like that I have done. You get how much is delta VO. So delta VO, which was for the first beam, was calculated 486 divided by EI. So first part of this compatibility calculation right now is clear. We know how much is delta VO. Now we need to calculate how much is delta VB. Okay, delta VB is a beam that has only a unit load over there. So it's more or less similar to the beam that I already calculated its bending moment here. Because if you want to calculate delta VB, so similar to what we did for this beam and what we learned from virtual work method, you need to have two structures. One structure is this one. The second structure is similar to the first one without this load, but apply unit load. So you can see the second structure is going to be exactly similar to the first structure for this. Because if you remove this one and you apply a unit load, the shape of the structure looks like the same structure. In other words, M and M bar is similar for this structure. If you calculate M bar will be exactly similar to M. This is similar to the calculation that we had here. So in order to calculate delta BB, we just have to calculate the bending moment here due to the unit load, and M bar exactly similar to M. So M and M bar are similar. Put it inside your equation, you get X as the bending moment, and then you put it back inside this equation, you get delta BB equals to 72 over EI. So right now, we know how much is delta BO, we know how much is delta BB, and finally, XP can be calculated, which is in the next page. Okay, so we go to next page. So delta BO, you put it the value there. Whatever is the sign, positive or negative, doesn't matter. You just put it exactly there. Plus XP multiplied by delta B, which is 72 over EI. And from there, you get XP positive 6.75. So this positive direction that you get is showing that in the previous slide, this direction that we assume for our unit load is correct. If you get negative, that means in reality, the force that you apply should be go toward down. So if you got positive, meaning the support reaction is in the direction of the unit load. If you got negative, that means the support reaction is in opposite direction of this force. Okay, so we got the support reaction, and then right now you can easily analyze this frame because we have only 3 unknown support reaction. And if you write down sigma m at point, let's say A equals to 0, or you write down sigma fy equals to 0, then you can easily calculate the support reaction, vertical support reaction. If you write down sigma m at this point equals to 0, we can get the bending moment. So you can easily analyze the frame after it becomes a determinate structure. This is the bending moment, and this is the shear force diagram. You can check at home. Okay, let me go back again. Just explain one more time that what we did. We got one structure. They asked us to analyze it and get the bending moment and shear force diagram. In order to do that, we assume one of the support reactions to be a known support reaction. In this case, we assume to be the support reaction at point B. Okay, now that we want to calculate the XP, we are going to remove it first. The structure will become a determinate structure. But since we have removed XP, we have deflection, we call it delta BO. And in order to deal with this delta BO, we need another structure that can push the structure up to its original condition. And we can write down the compatibility condition such that these two become similar. But since we don't know how much is this force exactly to make delta B equal to delta BO, we assume it to be X. So X multiplied by delta B plus delta BO should equal to basically 0 because we don't have any deflection in our real structure. So our job right now, in order to make the structure a determinate one and get XP, is to calculate delta BO and delta B. Delta BO comes from the first beam and delta B comes from the second beam. And you're going to use virtual work method in order to calculate these two deflections. This is what we have done in the second part. So as you can see, I have cut the beam from the right side, and then I've calculated how much is M. And if you want to calculate deflection, we said we need to remove the load and apply a unit load over there. This one gives us M bar. So we put it back inside the equation, and we can calculate our delta BO. Now we go for delta B. Delta B, we said, again, similar to delta BO, we are going to use virtual work method. So if you want to calculate delta B, your first job is to get M for this structure, and then get M bar for a structure similar to the first one without this load, but with a unit load. So that M bar basically is going to be similar to M, because if you remove this one and apply unit load there, these two structures become similar. That's why M and M bar for the second structure will be exactly the same. So if you look down here, this is going to be the structure that gives us M and M bar. And the moment that you calculate the bending moment, you put it back inside the original equation that we have, get delta BB. The moment that you got delta BO and delta BB, you just put it inside our equilibrium equation, and that is going to give us XP. And the direction of this XP depends on its sign. If it is positive, it's exactly in the same direction of load that you have applied. So we got 6.75, and after that is very easy. Sigma of y equals to 0 and sigma m equals to 0. You get the bending moment. Okay, so this is the first example. We will see another example after this. But before we see the second example, just now I said in the selection of that redundant structure, you should be careful because the structure after removal of that support reaction shouldn't be unstable structure. Some example of unstable structure and support reactions that you cannot remove is given in this example. Let's say here you have a two-span beam. So you have 4 support reactions, 2 roller and 1 pin. So one of the support reaction is unknown. If you select the horizontal support reaction of the first support, your structure become an unstable structure because it's going to be a 3 roller support. If you remove the horizontal reaction to calculate it through force method, your structure is going to become unstable because if you apply any load, it's going to move. So you cannot remove basically the horizontal support. Instead, what you can do, you can remove this support, like the one that you see here, and calculate it. Or you can remove this support and let the first one remain in this place. Another example is like the second beam here. So again, we have 3 support reaction and 2, and we have 1 internal hinge. So as I said, you can assume that the bending moment here is the redundant one, like the one that you can see here. But the moment that you put a hinge there, because when you remove the support reaction, you need to put the support reaction, meaning the bending moment here should be 0. So if you have a hinge, it's going to be 3 hinge. That is again become unstable. So for this case, you can assume that the bending moment here is the redundant one, and you can replace it with a pin support, and you will be interested to calculate how much is that bending moment. This structure right now is stable structure, and there is no problem with that. Or if you have a frame, this is a frame right now, you can see, you cannot remove the vertical support reaction here and obtain that XP. Because the moment that you remove the vertical support reaction, then your structure is going to look like this one. If you apply any force from up, the frame is going to collapse. So this structure become unstable. But instead of vertical support reaction, we can assume to be the horizontal support reaction, that it is redundant. In that case, your structure is stable and you can get XP, and then after that, you can analyze the whole structure. So these are 3 examples of the cases that the redundant support reaction can make your structure unstable, and you're not allowed to do that because the analysis is not going to give you a correct answer. And you need to select the right support reaction in order to analyze your structure. Okay, let's go to see another example. The same frame that just now we analyzed it, we have used another support reaction to get the bending moment and shear force. Before this, we assume that XP is the redundant, and we calculated the XP, and from XP we calculated the bending moment and shear force diagram. The same example have been solved, but this time we have assumed that the unknown support reaction or redundant support reaction is the bending moment at point A. So if you remove the bending moment at point A, your structure is going to change to a pin and a rotor support. So this one also is right now a determinate structure. But the problem is that the moment that you remove this bending moment, your structure is going to show some rotation over there. We know that fixed support in reality don't have any rotation. So the moment that you remove the bending moment from there and you convert it to a pin support, basically you have also change the zero rotation to a value that we don't know how much it is. So we need to apply this time a bending moment to that specific location and to make that rotation equal to zero. Because in the first place, in the same structure, we didn't have any rotation at point A. So here, our structure is going to look like this one after we remove the bending moment. And in order to get basically MA, we are going to have two structures. One structure is going to have the external force. One second structure doesn't have any external force, but it's going to have a bending moment at point A. The job of this bending moment is to make this rotation, delta theta A, equal to zero. But since we don't know how much bending moment we should apply to rotate back the structure in such that its rotation becomes zero, so we assume that we are going to have the deflection of delta gamma as a result of this unit load. So we multiply that one to MA or XA, the value that defines how much is going to be. And then we write down our compatibility condition. So this compatibility condition is exactly similar to the previous example. The only difference is that instead of having delta V and delta VB, this time we have theta A and theta or gamma A. So you can see gamma A multiplied by M plus delta theta A should equal to zero because we don't have any rotation over there. So our job is to calculate right now theta A and gamma A, meaning the rotation. So since we want to calculate rotation, we use the equation that we got for rotation before this. It was exactly similar to the equation that we got for deflection. The only difference is that we have here theta A. So in this structure, we need to see how much is theta A, and in the second structure, we need to know how much is gamma A. So if you want to calculate theta A from virtual work method, what we need to do is to analyze this structure, get the M, and then analyze the second structure that doesn't have this external load, but has a bending moment at point A with the intensity of 1, and then get M bar. So two structure has to be analyzed, one structure and two structure. So these are the structures. And then you can see in the first structure, we have only the external force. In the second structure, we have that unit load, unit rotation, basically, bending moment. From here, we get M. From here, we get M bar. And we put it back inside our equation. And from there, we can get theta A. So the moment that you got the delta theta A, the second step is to go and calculate gamma A, delta gamma A. In order to calculate gamma A, again, you need to have two structures. One structure under the unit load that it has there. And the second structure is going to be remove that unit load and apply another unit load. You can see here again, the equation of M and M bar for the second structure will be the same. So right now we can say that M equals to M bar, and the value can be easily calculated from writing down the equations of equilibrium. And finally, we get gamma A after you put all this calculation inside the integral. So you get gamma A, you get delta A, and you put it back inside the compatibility condition, and you get how much is MA. So if you know how much is MA, basically, if you know how much is MA, your structure can be easily analyzed because you have only 3 support reactions that we don't know. And you can get the same bending moment and shear force diagram. So in the second example that we saw just now, everything is similar to the previous one. The only difference is that we use the bending moment as the redundant support reaction. And when you use the bending moment as a redundant, so you need to calculate thetas because the bending moment there was before this 0, and now it has some rotations over there that the rotation was 0 before this. So that rotation needs to be calculated. And since we know that the rotation was 0, we use another structure. We apply a unit load, unit bending moment there. And if these two delta become similar, then this two structure is going to represent the real structure. So we wrote down our compatibility condition. We calculated theta A and delta A, gamma A. From there, MA was calculated. Okay, we have more examples to come. This is one example for the case that you have 2 degrees of indeterminacy. I will leave it for you to read at home. The procedure is exactly step by step, similar to what we did for the single degree of indeterminacy. But as I said in the exam and test, normally we don't give this equation, this type of example to you because the calculation is taking a lot of time. You need to calculate here 4 basically unknown parameters. It can be delta, it can be theta. So the calculations takes a lot of time. So that's why we don't go through this kind of questions during the test and exam. But if you were interested to know how a structure with 2 degrees of indeterminacy can be solved, you can read this question example, and if you had any question, we can discuss it in our next class. So this is just for your self-study. Okay. Here also is another example, again, with 3 degrees of indeterminacy that you can, again, 2 degrees of indeterminacy that you can basically use it in order to calculate the unknown support reactions. So for this case also, you need to write down 2 equilibrium condition based on the support reaction that you remove. And again, the calculation is going to take a long time. But the final result have been put here. If you are interested, you can do the calculation and see whether you get this result or not. Okay, so right now I will solve again one more example for you. So let me stop here and share with you another example. This is the question that was given to students in the previous semester. So you will see how we can use the force method or virtual work method in order to analyze this frame. So this one also have been uploaded in the e-learning, so you can download it and look into the calculations that we have done there. This is a beam. Here we have 2 spans, and our structure is subjected to 1 uniform load, and we have also a point load that has been applied 1 meter after support D. So our job here is to calculate the bending or to draw bending moment and shear force diagram for this beam. And we are going to use, it has been asked to be used the force method, and deflection should be calculated by virtual work method. Okay, how we are going to do that? Again, you need to assume which support reaction is going to be the redundant support reaction for you. And as we said, that support reaction shouldn't make your structure unstable. So for this specific case, normally in the exam, as I said, we tell you that which support reaction you need to select. So for this specific case, RB has been selected to be the redundant support reaction. So meaning we are going to remove RB, and after that, we are going to have 2 structures. One structure here is the one that doesn't have RB. So because RB has been removed, we have a delta beat over there. The second structure will be exactly exactly similar to the first one, but with this difference that we don't have any external load over there, and we apply a unit load to that location that the support reaction has been removed, so that we can push the displacement back to its origin. So if this delta B and this delta B are similar, these 2 structures is going to represent the original structure. In order to make these 2 similar, we can write down one equilibrium equation. That means this delta B plus x, that we don't know how much is it, multiplied by this delta B should equal to 0. Why 0? Because there is no any deflection or settlement at point B due to the support that exists there. In the exam, he may say to you, okay, we have 3 mm or 5 mm or 10 mm deflection at point, settlement at point B. In that case, you need to see, you need to know that this value is not 0 anymore because you have settlement. But since there is no settlement in this structure, so summation of these, the 2 deflections should be 0. So now you have 2 basically deflection to calculate. The moment you get delta B and the small delta B, then you can get x, that this x is basically that RB. Because this is the only case that these 2 deflection become similar. So let's go and calculate delta B and delta BB for these 2 structures. If you want to calculate delta B, this is the equation. So we need to know what is M, what is M bar, and we need to divide our structure into different segments because the bending moments are not similar for each span. So from A to B, B to C, C to D prime, and D prime to D are the locations that we need to calculate the bending moment for two structures. One is this structure that has the external force, and the second one is the structure that doesn't have external force but has a unit force at point B, which is similar to the one down here. So this is the calculations that I have done from A to B. This is the bending moment. Again, as we said, you can assume that the origin is here from A to B, from B to C. And if you want to change it from B to D prime and D prime to C, also you can. But for both structures, meaning a structure with external force and a structure without external force, you should have the same origin for any segment of your beam. So that's what we have done here. You can see the calculation of M for each segment, calculation of M bar for each segment, and after that you put it inside our integral and you get delta B. So the moment that you got delta B, one part of our equation has been already completed. We need to calculate for the second part, which is small delta B. A small delta B comes from this structure. So if you want to calculate a small delta B, you should divide this structure into two structures. One structure is going to be similar to the first one, you get the M, and the second structure will be this structure, but remove this force and put a unit force over there. This is what the visual work method says. So if you remove this force and put a unit force, again, you will see that M and M bar will be the same for this structure. So that's what we have done here. M and M bar are the same all over and for all the span, and you can easily calculate the values. So you got M and M bar, you put it back inside this equation, and you can get small delta B. So you have large delta B, you have the small delta B, put it inside comfortability condition, you get X. So the moment that X is clear for you, which is 56.8, the other support reaction can be calculated. Just write down sigma for Y equals to 0 and sigma at point C or D equals to 0. So you get the support reactions, then you cut and you can draw the bending moment and shear force diagram. So this is another example that has been uploaded into e-learning. So you can go through, and for our next class, if you had any question, you can ask. We have also one more example that shows how basically virtual force method can be used for frames, that I'm going to share this one with you in our next class. Since this is our first class, I don't want to make you too much tired. So we stop here and I will explain a little bit about our case study, and then our class is going to end for today. If you have any question regarding whatever I discussed until now, you can ask. And if there are parts that you need to review at home and you get some question regarding that, you can ask in our next class. So do you have any question about whatever I explained so far? If you have, please open your mic and ask your question.